Electrodynamics, magnetic fields, loop of a wire. We did this, several different videos on this, playlist down below. So if I have a loop of wire with a current, how do I find the magnetic field? On the axis, I can find it that way, but I can find it everywhere. Now, the question I want to talk about is, could we have used Ampere's law to find the magnetic field here? Could we use Ampere's law? Yes. Could we find the magnetic field? Not really. So just remember that Ampere's law says this. It says that the path integral of B dot dl around any loop is equal to mu naught times the current passing through the area bounded by that loop. Okay, so if we did this for a wire, so here's a straight wire like that, I can pick a loop, a circle around that, and I can calculate B dot dl because B and dl are in the same direction and B is of constant magnitude. And so B dot dl becomes a very easy thing to calculate. And then I crossing through there is just I that passes through that loop right there. So that's not too bad. We did it. But we can't do that here. Okay, let me draw a little picture. We're going to do it anyway. Let's draw a little picture. So here is my loop, looking at it from the side. And so the current's going into the board there. It's going out of the board there. I just picked. So into the board, we're going to get a magnetic field like this, a magnetic field like this, and overall, we're going to get this dipole field. Like that. Okay, so it has this shape like this. Could I pick a path to calculate the Ampere's law? Well, let's just pick over here a circle based on that. Can I calculate Ampere's law? Can I calculate B dot dl? I sure can, right? But here's B, there's dl, there's B, here's dl, there's B, here's dl, there's B, here's dl. So B and dl are not in the same direction, so it's not an easy integral. But still, the current passing through this would be 0 because I have I going out, I coming through, and they add up to 0. So B dot dl around that path should be 0. What if I pick a different path? What if I did a path like that around that circle? Well, still, now I have B dot dl, the integral is not 0 because there is a current going through there. But again, I don't have a symmetry that I can take advantage of to calculate that. So what I want to do is to take my loop and integrate B dot dl around a circle and show that it's approximately 0. Now we're going to do it numerically. Okay. So what I'm going to do is to take, I'm going to start right here, and I'm going to move in a circle, and each one of these will be dl. I can calculate B, I can calculate B dot dl, and I can add it all up. And we'll see if it is close to 0. Okay, so let's do that in Python. Now, I'm going to start with my previous code. So this is the code I made that shows the magnetic field due to a loop. And I actually did it 2 ways. I used the dipole moment, and I used just the loop. So that the magenta is the dipole moment. But we don't want that. Okay, but it does look cool. We're going to keep our loop, and we're going to delete all this other stuff. So I've already copied this code, so it's a new program. So that's fine, that's fine, that's fine. I can leave it there. I don't want to have all this stuff, right? I don't want to calculate that, and I'm just going to delete it. Now if I run it, I just have the loop. There's my loop. Okay. Now I want to move around. I want to take a new path. I want to move around in a circle in the XY plane, and then we can calculate the thing. So I'm going to actually do this in steps, just so we can see how it moves along. It'll be fun. So down here, I'm going to start off with RO is a sphere. Position is going to be equal to, let's move in a length of L. I'm going to put L is 0.3. So the position of this, and I'm going to make a new theta. I'm going to reset theta. I'm going to reuse theta as 0. So the position of this is going to be equal to L times cosine theta, L times sine theta, 0. And then the radius position is vector. I didn't do vector. And you can't see that because I'm a dummy. So there's my vector position. The radius, let's put as, radius is going to be L over 20. Color is color.cyan. Wait, what? Yeah, I'm going to do color is color.cyan. And then I'm going to do make trail equals true. Okay, so now what I want to do is to move this thing around. So let's say in, I'm going to reuse my in. I don't want to do the same thing. I'm going to do 100 steps. Yeah, 100 steps. So d theta is going to be 2 times pi divided by n. And then I want to say while theta is less than 2 times pi, rate 50. So it's going to take 2 seconds to do it. So rate 50 says don't do more than 50 loops per second. And now I'm just going to move my point. So I'm going to have the same thing. ro.pos is equal to vector. Vector. Do I have an extra? Okay, I'm just going to put the same thing. I think I might have an error in there. And then I'm going to move my angle, right? So I'm going to increase my angle. Theta is theta plus d theta, and that should do it. That should move all the way around the circle. I haven't calculated the magnetic integral yet, the line integral. Nice. Okay, my sphere is a little big. So let's make that a little bit smaller. Radius over 50. Okay, nice. And so that's 100 steps. You don't really see the individual things. I do need DL, right? I need the direction of DL for each of those step sizes because I'm going to do B.dl. So this is in polar coordinates. I'm not going to derive this. I'm just going to say it. So let's put down here DL, even though I think I may have used that before, so let's put DLO. It's going to be, I need D, let's call it DS. I did that too. That's fine. DLO is going to be equal to the length, which is L times d theta. Right, that's the step size, but I need it as a vector. So that's going to be times the vector negative sine theta cosine theta 0. So this is theta hat in Cartesian coordinates. This is the direction of motion in Cartesian coordinates. If you want to see where that comes from, I do have a video in that. I know I do. If you comment down below and like the video, you got to like it first too, right? That's all obviously true. And subscribe and hit that notification bell. I've never said that before, but I just said it. Then I will post a link to that thing down below, because otherwise I'll forget. So now DLO is the vector in the direction of motion, so that's good. Now, let's just go ahead and put an arrow there. So I'm going to make a new arrow called B arrow. Its position is going to be equal to RO. Its axis is going to be B scale times B of RO. Remember, we have that function B that tells us the magnetic field at any particular location. And then let's give it a color, is color dot magenta. And then so down here, I'm just going to move my arrow. So B arrow.pos is RO.pos. B arrow.axis is going to be equal to B scale, got to spell it right, times B of RO. And then so that should calculate the magnetic field. Still haven't calculated the line integral yet. And there's an error. B arrow is not defined. I just defined it. B arrow right here equals arrow. Still an error. ROT is not a function. ROT. Where did I put ROT? ROT is not a function. So I just did well, it had to be something over here because B arrow.pos, where is ROT not a function? Let's see. ROT. That's fine. That's fine. That's fine. That's fine. 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 How do I close that thing? There. ROT is not a function. Let's just print, did it make my arrow? Let's just get rid of the arrow and see if that works. Because we didn't have that in there before and things were working. Okay. Forget the arrow. So what I need to do is to calculate up here. I'm going to put amp b is 0. This is my sum of b.dl around the path, right? So I'm going to add to that, and that will be my, I guess it's called, I'm not sure what you'd call it. So now down here, I can calculate b.dl. So dbdl, I'll call it bdl, dl, is equal to dot b of ro.pos, and idl. No, it's just dl, which is dlo. And then I'm going to add that to my total. I'm going to call this bl. So my total is going to be bl equals bl plus dbl. And then I'm going to print that. Print. Let's just print it. bl. And there's an error. Can't access x of undefined. I think this is the problem. L d theta vector negative sine theta cosine theta 0. That looks fine. B arrow is ro.po. Oh, I know what I did. I have ro as a sphere. No, that's fine. It did make the sphere. Dot b of r. Oh, that's wrong. That's the problem right there. So b of ro.pos dot dlo. And let's turn these off because I don't know what these are doing. Right, so that b, that's right. That should work. Please work. Went around, that's good. And I get a very small b.dl, so it is close to 0. Now, if you want to do the other loop, like go near this other thing, it's a little bit trickier because you have to shift your circle around, and it's not so easy to, it's not impossible, but I don't want to do it. But here I'm showing you that b.dl is indeed 0. There's total current passing through the thing 0 also, so we're all good. The end. Link to this code down below. Again, if you have any questions, just let me know. I'll be happy to answer them in the comments, and I'll talk to you later.